Okay, so we are currently recording, and you guys have found this question. I'm going to drag that guy there, bring up the paint tool. Okay. Hang on a second. There we go. Okay, so you guys are looking at this one, and with this guy here, obviously the electrochem stuff we've been tackling kind of shows up at the bottom, but it all ties together with oxidation states and things like that. So they give you this equation up here, the 2Al plus the 3Zn plus 2, go into the 2Al3 plus the 3 zinc metal. And it says respond to the following statements about the reaction. First thing it wants is the complete electron configuration for the Zn plus 2. All right, so remind me again, what's an electron configuration? They give you a hint.
It's the 1s2, 2s2, 2p6.
Yeah, right. And the periodic table, all right, lets us look at that, right? So we go and we find it, and we use the trick from the periodic table, but you got to be careful. Whenever we're looking at something like Zn plus 2, whenever it's an ion, you have to remember what we do is we write out the normal configuration for Zn, then you take 2 away. You want to avoid the temptation to go to the periodic table and then just move 2 spaces back, because you have to remember, where do the electrons that leave always leave from?
The outermost orbital.
Exactly, the outermost orbital. So if you guys are looking on a periodic table and we were to write the Zn plus 2, we start with just Zn's config. All right, and that's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then regular zinc is 3d10, all right, because zinc is element number 30. All right, we get 2, 4, 10, 12, 18, 20, 30. All right. So like we said, all right, the first 2 electrons come from the highest level. So Shane, I see your name popping up there. All right, Shane, you with us?
I am.
All right. Where are the first 2 electrons leaving from to give me my +2 charge?
Would it be the 3d10?
Nope. What's the highest number you
Oh,
see
no.
in front?
It'd be the 4s2.
Exactly. So that's like kind of a trap question. You guys just got to make sure you find the highest level, and there's 2 electrons in that, so it's the 4s2 that goes. So the real config is just going to be this guy with the 4s2 gone. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. All right. Questions on that first one? All right, so second question, letter B, says which species, right, the Zn or the Zn plus 2 has a greater ionization energy, and then justify why. You have to support it with why. So start simple, all right. Carm, I see your name pop up. You with us?
Yes.
Do you remember what ionization energy is?
Kind of, but not really.
All right, take a crack at it. Let's see what you think.
I have no idea.
So it's about taking something away. It's how hard it is to take something away.
Electrons?
Exactly. So it's asking you, who is it harder to take an electron away, the Zn or the Zn plus 2. So if we want to figure out who it's harder to take an electron away from, right, we need to figure out who's got the bigger Zeph, who's got the greater nuclear charge. All right. Angel, do you remember what controls nuclear charge?
Isn't it how strong the protons pull on the electrons?
Exactly. So usually we'd look at protons to start, but the trouble is they're both zinc. So they both have 30 protons pulling in. Whenever they have the same number of that stuff, what else do we have to factor in? So we've got the number of protons. but
How
what
many
else?
electrons?
How many electrons, exactly. All right, so the normal Zn has 30 electrons. Zn plus 2 has 28 electrons. And like I said, this all ties together. All right, so if we look at this guy right here, right, if I'm taking, and I'm going to put the 4s2 in right here so you guys can see the difference between the zinc and the Zn plus 2. If I'm taking zinc's, regular zinc's electron, all right, Ethan, where is zinc's first electron leaving from?
Which one? The Zn plus 2 or regular zinc? You would take it from the 4s2, right?
Exactly. So this guy's first electron is leaving a 4s orbital. All right, Eth, where is Zn plus 2's first electron leaving from?
From 3d10.
BD. All right. So then you guys are just saying, okay, well, whose electron is going to be, they wanted greater, whose electron is harder to take? It's got to be this guy, right? Why is that guy's electron harder to take?
Because it's in a closer orbital.
Exactly. All right. So you guys want to jot this down. All right. Zn plus 2 has the higher ionization energy. Because its electron is leaving from a sublevel closer to the nucleus. Anybody need a repeat on that guy? Okay. All right, pushing into letter C. It says identify the species that is oxidized in the reaction. All right. So Camille, talk to me about oxidized. What do we look for oxidation?
Losing electrons.
Good, right? We're talking Leo and Gur. So we're looking for losing electrons. So we have a reaction. I probably can't copy that. But we have a reaction. So we've got Al turning into who, Camille?
Al plus 3.
Good. And then you've got Zn plus 2 turning into who?
Zn.
Good. Okay. All right. Take over from there, Alexandra. So for Al to go to Al plus 3, where do the electrons live?
They're going on the Al plus 3 side.
Good. And for the Zn plus 2 to go to Zn?
It's going to go on the Zn plus 2 side.
Okay. So which one of these is losing electrons?
The Al.
Exactly, the one with the electrons on the right. So there's my loss of electrons. And remember, the species that's oxidized, reduced, the agents, they always come from the left. So you're going to say it's the AL. All right. And it didn't even ask to justify. All you have to do is say AL. And so for C, just write AL. All right. Questions on that one from you guys? All right. Pushing into the bottom section. All right, so down here, all right, looks like we've got an electrochemical cell. All right, it says the diagram includes a salt bridge filled with, all right, KNO3. Describe what happens in the salt bridge as it operates. So, Sydney, all right, remind me what the salt bridge does.
So what was that? I have 2 Zooms going on at once.
Oh, geez, what class are you watching?
History of Broadway.
Oh, good gracious. Okay. So, remind me what a salt bridge does.
That's where like the protons will transfer. It'll go from like the right to the left.
Yeah,
Oh, wait.
exactly. So the
Yeah.
positive ions move one way and the negative ions move the other, and that stops the electrons from building up at the cathode. All right, so the key to remember with those is that the positive ions, which are our K pluses, chase the electrons. All right, so take over from there. Take over from there, Abby. All right, so in our, wait for it, that's what I do. Hang on a second. I didn't X out of that, did I? Wait for me. There it is. Sorry. Okay. So Abby, all right. Which way are our electrons flowing in our picture?
To the right.
To the right, because you knew that the Al was oxidized, which means this side here is my anode. So the electrons are going left to right. And which ions chase the electrodes or chase the electrons?
NO3.
Electrons are what charge?
I don't know. I'm confused what you're asking.
So start simple, right? So hang on, it helps if I get the picture, right? So we've got our salt bridge there, and then you told me the electrons are moving this way in the wire, right?
Yeah.
Okay. So electrons are negative. So which ions in the salt bridge are going to chase the electrons?
Oh, the positive, so the K plus.
There it is. So the K pluses are going to be moving to the right in the salt bridge, and the NO3 negatives are going to move to the left in the salt bridge. All right, and that's what you're going to say there for letter D. All right, so if I were you, I would sketch this picture right here. All right, and then it says describe what happens. It probably would get you the points for just the picture, but let's just go ahead and say it anyway. The positive ions move toward the cathode. The negative ions move toward the anode. Questions on letter D? Okay. All right. Let's move on to E. So E wants us to get the standard voltage, the cell potential for the cell. All right. Jan, talk to me. How do we usually get cell potential?
Oh, is it using an equation to? They didn't give us these voltage, so we need to find something. Use a different equation.
Exactly. So they're going to give us, the AL going to AL plus 3 electrons, right? And if you have an equation like we do up here, you guys are forced to use it the way it's written, right? And we don't care about coefficients because the coefficients don't change it, all right? The only thing we do care about is if we flip it, because if we flip it, the E cell goes from negative to positive. All right, so I get my 2 electrons in there. Now, on the exam, you guys will look up these values. Okay, right? Like you would have a sheet, and if I can find it, I'll share it with you. But if not, you can just look them up. So you got to look at standard reduction potentials. Okay, and give me a second. There's a chance I might be able to show you that. I have it somewhere. Sometimes I have it. I do not. All right, so I'll jump out here real quick, right? Standard reduction potential. All right, so you find one, and we're looking for our reaction. So here's one of them, right? It's Al plus 3 electrons going to Al. That's negative 1.66. Al plus 3 electrons. So that one is written backwards. So what do we have to do to our negative 1.66?
Make it positive.
Exactly. But because it was written Al plus 3 electrons to Al, and we have the reverse of that, this guy becomes positive 1.66 volts. All right, now I'm looking for Zn plus 2 electrons going to Zn. So I scan Zn plus 2 electrons to Zn. That guy's negative 0.76 volts. And we didn't flip it, so it stays. So negative 0.76 volts. All right, do the math there, and it looks like your cell potential is going to be 0.90 volts. All right, questions on that one there, which was the cell potential.
If we would have to look up the values, like is it in the book or is it like online?
Start in the book, right? And I'll get some info your way. I'll poke around in the book and see if there's one. 796 has pretty much anything you would need, page 796. But I'll look around. And like you said, you can always look them up online. And as long as it's close to the real number, like I'll do the math to make it work.
Do you have any sort of like website or place to look in case it's online?
Yeah, I might share it with you so we all just use a uniform one. So like I'll share a link with you guys so you know which chart to be using. But let me see if I have like an electronic copy that I can just give you guys first.
All right, thanks.
Sure. All right, so we've got positive 0.90 volts. Any questions on that? Okay, so now we're into letter F. It says indicate whether the value of the standard free energy change, delta G, is positive, negative, or zero justified. You don't need to do any additional work. You guys know right now, based on what you're seeing with this guy, whether or not the delta G is going to be positive, negative, or zero. But let's refresh our memory real quick on scenarios of that. All right, so if we look at that guy, Elena, right? Do you remember what it means if you have a positive voltage?
If you have a positive voltage, it means the delta G is going to be positive.
Tell me why.
Because the equation is delta G equals negative NFE.
Now do that math.
What is the F a constant?
Yes.
I don't know what the constant is.
Doesn't matter. It's not asking you what is the delta G. They're just asking, is it positive, negative, or zero?
Oh, it should be negative. Delta G will be
Negative, because
positive. Because the negative in front of the N.
exactly, right? So positive voltage means that it's thermodynamically favorable, and that means negative delta G, right? So you could just say positive voltage means spontaneous, which means delta G must be negative. That's like a standard fact. You could do what Elena did and said like, hey, minus NF cell, right? This is moles of electrons. That's a constant. The E cell's positive, right? Positive, positive, positive. The negative, it would be negative. All right. So I would just do it in word form for this one. And I would say for the answer, all right, the delta G is negative because a positive voltage indicates it is thermodynamically favorable. All right. The positive end of that is just the flip, right? If this term here had been negative, that means not thermodynamically favorable, right? Which would have led us to a positive delta G. And then last but not least, when is delta G 0?
Well, that's standard states. Oh no, it's equilibrium. That's it.
Equilibrium, right? So if this were an equilibrium, right, the delta G would be 0, right? And you would have to, have some data to do that. But that's just the little link between each of those. All right, finishing out the question. It says if the concentration of AlNO33, all right, in that Al half cell is lowered from 1.0 molar to 0.01 molar, does the voltage increase, decrease, or remain the same? So this is a Nernst equation type effect, but you don't need to run the math, right? You guys just need to see what happens to your cell. So you've got your cell, right? He's running this. You guys already told me the electrons are going this way, right? Right? You know the voltmeter's reading 0.90 volts. Here's my AL side. Here's my ZN side. All right. They're saying that in this half, I lowered the concentration to 0.10 molar, right? So what we did was we made the Al plus 3 concentration decrease. All right. So if you look up here, where does the Al plus 3 concentration live?
On the left.
Careful.
Oh, right. Sorry.
On the right. If I decrease on the right, it causes a shift.
Right.
Right. And if we move in the direction it's written, the E cell increases. Right. So one answer that you could attack it would be E cell increases, like decreasing the Al plus 3, like shifts the equilibrium to the right, increase in the E cell. The other thing you could do is you look at this. The ZN's 1 molar, and this guy's 0.1. Remember how concentration cells work. What's this guy going to do? Right?
It's going to gain.
Yeah, these guys try to become equal, right? Right? So like in a concentration cell, these molarities try to equal out. So the Zn plus 2 wants to decrease, and the Al plus 3 wants to increase. So think about it. How do I decrease the Zn plus 2 concentration? Right? How do we lower the Zn plus 2 concentration over here?
You increase some electrons and make it metal.
Exactly. More electrons come over, these guys combine, and we plate out zinc metal. Right? Which means more flow to the right. And the same is true here. How do I increase the Al plus 3? Al metal releases electrons into the wire and falls into the solution as Al plus 3. All of those are moving electrons this way. And if you're flowing in that direction, your E cell increases. All right. Questions on the 2010? Okay. All right. Let us jump to. Where do I want to go? All right. All right, let's go to. I want to do another one like that. All right, go to 2012. Hey, Gabe and Scarlett, you guys mind playing outside or upstairs? I'm trying to work. Oh, I was just getting my shoe. That's okay. All right, no big deal. Okay. Ah, there we go. I'll be able to do this for you guys. This is what you guys have. Like, you'll get this list. Right? It's in the equation portion of the exam. All right, so I'll be able to copy and paste this and give it to you guys. And so you guys will be all right. There we go. Okay. All right, so this guy here, don't worry about the top half. We'll just focus on the bottom, right? The electrochem part. All right, so diagram below shows your electrochemical cell. You've got a PB electrode, right, immersed in 100 mils of 1 molar PbNO32, and some electrode of metal X, which we don't know, and 1 molar of the X plus 2, which we don't know. Salt bridge has KNO3 in between it, right? And they tell us it connects the anode to the cathode. The electrodes connect the external circuit, this guy here, all right, containing a switch which is open. When the voltmeter is connected and we close the switch, we're reading 0.47 volts. All right, when the switch is closed, electrons flow through the switch from the PB to the X. All right, so that right there tells you a lot of info because they told you the electrons flow from the PB to the X. Right. John, which side is your anode and why? John, you still with us?
Yeah, sorry, my dad was in the room, so I didn't hear what you said. Sorry.
No big deal. All right, so based on what they told us with the electron flow there, which side is my anode and why?
The right side.
Tell me why.
Oh, it's because it's receiving electrons.
And gaining electrons is
not reducing. It's no. I forget.
It's all right. So this side is the GER. It's gaining electrons, which is reduction. And
Yeah.
remember, reduction, it's the red cat. So
Okay.
that makes the right side the cathode. And the left side is losing the electrons, which makes it the oxidation, which makes the left side my anode.
It's just the fact that it's saying reduction while adding stuff to it is like really confusing to me.
So think of it this way. It's reducing its oxidation state, and it does it by gaining electrons. Right? Because
Okay.
X plus 2 is gaining 2 electrons to reduce its oxidation state to X0. So that's another, that
okay.
might sort things out if you think of it that way.
Makes sense.
Okay. So now you guys know who your anode, who your cathode is. All right. So the question says, write the equation for the half reaction that occurs at the anode. So we know who the anode is. Now it's just about picking the right stuff there. All right, Shane, what substances are at the anode?
The NO3 negative and the PB plus 2.
So you got the PB plus 2, and you have NO3 negatives in there. And don't forget, who's the metal?
The PB.
The PB. So the NO3 you don't really care about. He's just floating around. So we would be focusing on that half reaction. Now, for this guy to be losing electrons, right? This has to be losing electrons. Where do the electrons have to be?
On the left.
That would be gaining.
Oh, on the right.
On the right, which means we have to be looking at this. The PB going to the PB plus 2 plus 2 electrons. So there's our half reaction right there. All right, PB arrow, PB plus 2 electrons. That's the equation for the half reaction at the anode. Okay, so they tell us in C that the value of the standard potential overall is 0.47. And they want to know what's the reduction potential of the substance for the X, right? So you already know part of what you need. All right, so if I clear this out, all right, you guys told me one of my half reactions is this guy, PB going to PB plus 2 plus 2 electrons. All right, we go back up here. We see what that potential is. All right, so you look in here. All right, you scan. All right, where do you guys see PB and PB plus 2 at?
Under the H2 plus 2 electrons.
Right here. Is it written the same way or is it backwards?
Backwards.
Backwards, which means what do we do to the 0.13 negative?
Flip it.
Flip it. So we know that is that. Now, we also know what the other one has to be, right? So based on that, Camille, what has to be my half reaction for the other side? Right? What's this half reaction have to say?
It's going to be the X plus 2.
Mm-hmm.
2 electrons going to X.
Good. Right? So we know that, and we know it's charged because they told us it was X plus 2. We knew it was X. That's where she's getting those from. All right. So, and that's just going to X metal. Okay. We don't know what that is. That's what they're asking us. But we know when we add them together, what does it have to be?
0.47.
0.47. Right? So what does this guy have to be when we add those together?
0.34.
There it is. So 0.34 volts is what that number has to be. So how can I use that to figure out who it is?
You can look at that list.
We sure
and
can.
find the
So
process.
if we go up here, we scan, we find 0.34, right? Who's 0.34?
Copper.
There it is. So you guys know it's copper because the 0.34 matches the 0.34 here. All right, so that's how we figured out that that was copper. All right, so that's what was going on with. Oh, right there. All right, that was I, and we got the half rate. So the 0.34. All right, that's letter I, and then the copper is II. And then last but not least, it asks, describe what happens to the mass of each electrode as it operates. All right, so you know the lead is becoming lead plus 2 and giving away 2 electrons. You know that X plus 2s are turning into X over here. So what has to happen to this electrode's mass?
Decrease?
It's going to decrease because you have lead metal becoming lead ions. And what's going to happen to this electrode's mass?
Increase.
Increase because X plus 2 swim up, they gain 2 electrons, they become the metal, so we're plating out on here. All right, so you would say the PB electrode decreases in mass. The Cu electrode increases in mass.
Wait, did you say the Cu decreased or increased?
The Cu increases. It gets heavier. Right? Because Cu plus 2 swim up, they gain the 2 electrons, and they become Cu metal. So we're depositing Cu metal onto this electrode, so it gets heavier. All right. Other questions on that one? Okay. All right, let's take a look at, find your way to 2011. All right, and we're looking at question 3. All right, and again, don't worry about the top half of this. All right, useful information, delta H and all that, but we'll tackle all that during AP review. Let's focus on just the stuff related to this chapter. All right, which gets us kind of halfway down. All right, so this guy here, it says we got a fuel cell, all right, and it's an electrochemical cell that converts the energy into electrical energy. A cell that uses H2 as the fuel can be constructed based on the 2 following half reactions. And notice, these guys are written both as reductions, right? So you are able to pick, all right, the way this reaction is going to be written, but you also don't forget, you have an equation up here that would help you along. All right, but either way, if I'm going to write a equation for the overall reaction, all right, who stays and who gets flipped based on what you guys are seeing for your E cells? Who haven't I picked on yet? Mia. Right, so you look at those E cells, who stays and who flips.
Would you flip the bottom one?
Good, because the more positive one stays and the less positive one flips. So the top equation is going to stay the same. So it's the 2H2O plus the O2 plus the 4 electrons going to 4 OH negative. All right, that stays as 0.40. We're going to flip the other one, which is going to be the H2 plus the 2OH negative going to 2H2O plus 2 electrons. And flipping the equation makes the voltage change from negative to positive. And I can calculate that right away. I know right away this is 1.23 volts because no matter what I do to this equation from here, I won't affect the voltage. Timesing it won't do anything. But we do need to make the electrons equal and opposite before we add them. All right, so Carmen, what do you have to do to the reddish colored equation to get the electrons to be the same?
You have to multiply it by 2.
Good. So we do 2 there. That guy's going to become a 4. He's going to become a 4. Oh, sorry. He didn't have a 2. He was a 1. He's just a 2. And the electrons become a 4. All right. And then we'll add up from there. All right, Alexandra, what are your electrons going to do? Here and here.
They're going to cross out.
They're going to cross out. Anything else you see that's going to cross out?
The 4OH.
The 4OH is going to go. So those go. And, oh, that's why. Sorry, this was, my apologies. I couldn't read this paint writing. So this was a 2, but it wasn't H2, it was H2O. All right, so this was 2H2O. And then when we times it by 2, it became 4H2O. All right, and the moral of that story is we had to have that right so that we could see the other thing. Yun, what else is going to simplify?
The 2H2O on the left got canceled out and left 2H2O on the right.
Good. All right, so then we end up with 2H2 plus an O2 going to 2H2O. All right, so that right there is D and E. All right, you guys did both. All right, because as soon as we get that equation, we know the voltages. All right, you guys just add them together, and that is what the standard potential, all right, for the cell is going to be. All right, questions on D or E? All right, F is the reason why I wanted to do this one. We haven't done one like this yet. It says, assume that 0.93 moles of H2 is consumed as the cell operates for 600 seconds. And then it says, calculate the moles of electrons that pass through the cell. All right, so these are plating problems. Anytime you see time involved, it's a plating problem, which are just bracket problems like we were doing on Friday. All right, where you either start with an amount and you try to run it to time, or you start with time and current and you try to get it to the amount that plates out. So what we know is we want the moles of electrons that pass through the cell, all right? And what they gave us were the moles of H2. So we've got 0.93 moles of H2. And we want that to be what? Not H2. What are we looking for in this letter here?
Electrons.
Moles of electrons. So it's a mole to mole ratio, and we get those numbers the same place we get any mole to mole ratio, from a balanced equation. So you look up here, which half cell has the H2 and electrons in it?
The second one.
Yeah, the second one. So this guy here has the H2 and the electrons. And it doesn't matter whether you use this one over here or you use this one, because the ratio is going to be the same. If I use this one here, I put a 1 with H2 and I put a 2 with the electrons. If I'd use this one here, I put a 2 with H2, but I put a 4 with electrons. So it's either 2 over 1 or it's 4 over 2. You could have used either one of them after you balanced it or before. All right, and it was a really small portion of the bracket problem. All they wanted us was to convert the moles of H2 into moles of electrons. So if we do that, you're just doubling up that number, right? 0.93 times the 2 ends up becoming what?
1.86.
There it is, 1.86 moles of electrons. Questions on that one? All right, so the next one says calculate the current, right? And we didn't do many like that. I either gave you the current, all right, and you got the mass, or you were getting a mass and using the current. All right, so if you were to see that on the AP test, all right, what I would say is jump to the equation sheet, right? If I'm trying to find something, I'm not sure how to get it, see if there's something on the equation page that can help me. All right, so I start scanning through here and we try to find stuff about electricity. All right, here's a section on oxidation reduction and electrochemistry. So I've got a Q, which looks like products over reactants to the power of the coefficients, right? That we know that. I've got this I equals Q over T, and you're like, what the heck are these, right? Well, they give you this list of what these things are. All right, bingo. I is current, Q is the charge in coulombs, and T is the time. All right, so that's what I'm going to use for this. So I equals Q over T. All right, so we start looking. All right, back to our question. All right, do we know the current? Do we know what I is? Right,
No.
They do not. And that's what we're looking for, right? They want the current. All right, so that means I should know Q and I should know T. All right, either of those standing out to anybody?
Isn't Q a constant and T we already have 600 seconds?
T is 600 seconds. Q isn't a constant, though. Q is the coulombs that pass through the cell. So we currently have that we moved 1.86 moles of electrons. What we need to do is make that be coulombs, which is built into some of those bracket problems we've done, right? We do moles of electrons to coulombs. Anybody remember what that link is? I'll give you the first number.
96,500.
Yeah, 96,485 or 96,500. All right, so we do that. Run the math on that. Hang on, gotta take out my calculator. 96,500 times the 1.86 looks like we're getting 17,900 coulombs. And that's what we plug in up here. Divide that by the 600 seconds, and you're going to get 29.8. And remember, coulombs per second is amps.
Mr. V, should that number for the coulombs after the bracket problem been 179,500?
I don't know. Let me check my math. Oh, absolutely. Yeah, 179,000. My fault. Right, because it's already 100,000 times 2. So add another 0 there, which moves this decimal one more. So 298 amps, I'm assuming. But let me double check the math on that. Yeah, 298 amps is what we were looking for there. All right, good catch, Hermia. All right, questions on letter F. All right, and G is just one of those random questions that sometimes they drop in, right? Some fuel cells use butane rather than hydrogen. The overall reaction that occurs in butane is listed there. Like standard combustion reaction, what's an environmental advantage of using hydrogen as opposed to a hydrocarbon such as butane? So this isn't even as much as chemistry related as it is like environmentally related, like what they're saying. So what's the problem with burning hydrocarbons that we know that happens?
It releases CO2.
There we go. That we create greenhouse gases, all right, which they think is the main cause of what?
Global warming.
So that one right there, G, I would just say, right, burning methane, or I'm sorry, butane, burning butane releases CO2, which is a greenhouse gas, and contributes to global warming.